Hi everyone, it's a pleasure and an honor to be with you today. We are a team from Toulon University in France. Our team members are Florent Barthélemy, who is going to be our patient today, then Pierre-Alexandre Peyronnet, who has moved to Paris for his studies, and me, Sebastian Marzetti. Our project is an artificial ventilator, low-cost, embedded, unsupervised learning for hardware failure monitoring. On 11 March 2020, the World Health Organization recognized COVID-19 as global pandemic. Even with physical distance and lockdown measures, hospitals were already reporting shortage of key equipment, including artificial ventilators. And this was particularly critical in developing countries, where medical equipment is difficult to supply. Several projects of artificial ventilators were proposed around the world, but they were focused on supplying developed countries. With our mentors, we decided to focus in a different challenge, helping people by creating an artificial ventilator low cost, which can be built everywhere in the world only with easy to find and low cost materials. So let's now show it. This is our artificial ventilator. It is made with 3 air bellows made with inner tire tubes. Then they are controlled by 3D printer stepper motors and connected with fishing wires. Mechanics as well as embedded electronics has been designed and manufactured by us, including some tricky sensors such as a pit-up tube for monitoring tidal volume. The artificial ventilator is connected to a PC where the control interface is running. Okay, we could stop. This ventilator is complying with medical requirements. It can be used in reanimation mode or in breathing assistant mode. Intra-lung pressure and tidal volume are adjustable and monitored. It has been tested on an artificial lung at IRBA, the French Defense Laboratory. Now, we will focus on one of the most important features on a medical system, robustness. Low-cost recycled materials quality is unknown. They may break at any time. Therefore, in order to improve robustness, we have developed a solution based on cooperation between embedded artificial intelligence and medical staff. As I just said, using low-cost recycled materials may lead to hazardous behavior, including mechanical failures. These failures cannot be avoided, but can be detected using a smart embedded failure monitoring system. The goal of this system is to learn in a very short time the behavior of the system composed by the artificial ventilator and the patient. After an initial learning phase, system enters in a failure detection mode, generating alarms if several successive anomalies are detected. So medical staff will take appropriate measures in case of an alarm. It is important to note that system behavior highly depends on patient state. Every patient is different. Thus, it is not possible to learn this behavior once and for all. Consequently, online unsupervised learning is initialized each time a new patient is assisted. Moreover, life of the patient cannot depend on the serial link between the embedded microcontroller and the computer interface. Thus, unsupervised learning has been implemented directly inside the embedded microcontroller and not on the supervising software, leading to a robot system based on a microcontroller. Now, let's start the demo. It is really live, so we hope that everything will work okay. We are going to learn the behavior of the system composed by Florent, our patient, and the ventilator. First, ventilator is in learning phase. We can see the samples arriving represented by yellow bubbles. They correspond to inhalation and exhalation patient cycle features. In the first stage of this learning phase, distance of the first samples is used for evaluating the data dispersion and adjusting automatically initialization cluster size. In a second stage of this learning phase, we can see the cluster generation and reinforcement. They are presented by the dark red bubble. This one has a variable size depending on the data dispersion. After approximately 1 minute, the learning phase is finished, so let's wait for it. We can see the samples arriving to the different clusters. That's it. We reached the monitoring phase. We will be able to test the failure detection by generating an anomaly. But before that, in normal mode, you can see that measured features are classified in one of the two existing clusters. Now, let's generate an anomaly. Florent, please block the reading host. You can see that anomalies counter is incremented. Background interface color also changed. And after successive anomalies, an alarm will be generated for warning the medical staff. Now, at the moment, we had 3 successive anomalies. When we reach 5, an alarm will be generated. We can listen, and the background is red now. Now, let's stop the demo and conclude this talk. Really high sound. So, what is important on a medical system? First of all, of course, we have to comply with medical specification. But we think that robustness is also a key feature. For this reason, we have proposed and demonstrated how to increase the robustness of our low-cost artificial ventilator by 2 means. First is to use unsupervised learning by learning system behavior and generating alerts. Second is to implement it directly into the microcontroller so that it works properly, even in case of a computer crash. Finally, result of our project is a low-cost artificial ventilator that can be produced everywhere, having a good robustness using the embedded artificial intelligence, of course. So we started this project with the idea of making something able to help people everywhere. Now, this project is shared as a free and open source project from mechanics to electronics, including embedded and monitoring software. We will be very happy to help any people wanting to use it or to improve it in any way. Let's fight COVID-19 pandemic all together. We'll be stronger. Thank you for your attention. We'll listen to your questions.